You know that crackle of static when you tune an old radio between stations? Now imagine that sound on steroids. And you now have an idea of what Jupiter's decameter radio bursts sound like. If you were strapped into a cosmic roller coaster barreling through Jupiter's intense magnetic field, you would experience something like this. As its volcanic moon Io orbits, it spews sulfur and sodium ions into Jupiter's magnetosphere, electrifying the environment like lightning arching through a power line. When these charged particles slam into magnetic field lines, they trigger powerful radio emissions in the 10 to 40 megahertz range, which is way below human hearing. But when we pitch them up, it sounds like a space DJ scratching a record. One moment you're drifting through silence, the next you're bombarded by wild, crackling bursts that pop and hiss like popcorn in zero gravity. Scientists aboard the Voyager and Cassini probes recorded these bursts as brief, intense squawks, sometimes lasting mere seconds, sometimes spitting out volleys of pulses in rapid-fire succession. Imagine a swarm of angry cicadas on amphetamines, then warp speed them up to interplanetary scale. That's Jupiter talking. The hidden dance between this planet and its moon is choreographed by magnetic forces you can't see but can definitely hear. They remind us that our solar system isn't a silent, empty void. Instead, it's a harmony of several forces. So the next time you scroll through radio stations and complain about that static, remember, somewhere out there, Jupiter is hosting a jam session millions of miles wide. If you had the right receiver, you'd be in the front row at the loudest concert in the solar system. It's like the bass drop at the universe's wildest rave, only it's reverberating through space instead of a nightclub. Picture Cassini, the space probe, drifting through the shadowy gaps of Saturn's rings, headphones off, and suddenly you hear a low, pulsing thrum that could rival any subwoofer. These emissions span the 10 to 1,000 kilohertz range, thousands of times lower than Jupiter's decametric squawks. When we pitch them up into our audio sweet spot, you get sounds like a deep, rhythmic heartbeat mixed with distant tribal drums, as if the planet itself were keeping time. The sound comes from charged particles, electrons, and ions caught in Saturn's magnetic grip. They spiral along invisible field lines, slamming into denser plasma regions above the poles. Every collision sends ripples of radio waves outward, forming bursts of pulsating tones that wax and wane in intensity. When Cassini tuned in, it captured chapters of these loud noises, gentle thumps, then a crescendo of rapid-fire raps, followed by eerie silences, only to kick back into the groove. These kilometric rhythms map the architecture of Saturn's magnetosphere, its strength, twists, and hidden twists where charged particles pool. They hint at how solar, wind, and ring material tango with a planet's own magnetic force. Basically, Saturn is much more than a beautiful set of rings. It's a cosmic drummer laying down grooves that scientists decode to understand planetary weather on an epic scale. Have you ever felt a whisper so faint you almost dismissed it until you realized it carries the roar of an entire star? That's the solar wind's plasma oscillations slipping through space like cosmic static on repeat. The sun is constantly hurling billions of charged particles, protons and electrons into the void at speeds north of 1,000,000 miles per hour. As they flood the heliosphere, these particles jostle against each other, setting up rhythmic pressure waves. When spacecraft like WIND and ACE park themselves between Earth and the Sun, their instruments pick up this subtle hum in the kilohertz range. We sample those frequencies and again pitch them into our audible realm. Suddenly, you're enveloped in a continuous, strange drone that quivers like a haunted violin across a cave. Some moments it quakes with a low, mournful groan. Other times it rattles with jittery excitement, with every shift in the sun's activity subtly modulating the tone. Beyond the goosebumps, these sounds are our frontline weather report for space. They reveal shock fronts from solar flares, the arrival of coronal mass ejections, and even the shape of Earth's protective magnetosphere as it braces for impact. Scientists break down those wave patterns to predict geomagnetic storms that can fry satellites, disrupt power grids, or transform the aurora into a celestial light show. Have you ever caught yourself daydreaming about northern lights painting the sky? Believe it or not, those rippling curtains come with their own soundtrack, something we call Earth's auroral chorus. When charged, solar particles slam into our magnetic field. They excite electrons in the upper atmosphere. Those electrons then oscillate, generating radio waves in the 0.1 to 10 kilohertz band. Pitch those up by a few octaves, and what you get is an uncanny chorus of whistles, chirps, and trills, like a flock of cosmic birds nesting in invisible branches. Probes, such as IMAGE and ground stations in Alaska, have recorded this. 1 minute you'll hear a slow, mournful whistle fading in and out, and the next you hear a rapid-fire series of sparrow-like tweets erupting in staccato bursts. It's as if Earth itself were humming a lullaby, then breaking into an excited chatter whenever a solar gust passes by. These harmonics do more than serenade aurora chasers, actually. Scientists parse the shifting pitch and tempo to track the dance of geomagnetic storms, which are known to knock down GPS signals, scramble radio communications, or even spark currents in power lines. In that way, the auroral chorus serves as both a celestial concert and a warning signal. So next time you lose signal on your car radio or gape at dancing green lights overhead, remember that Earth is playing its own soundtrack, forged by solar fury and magnetic might. If you had the right receiver, you'd be tuning into the planet's most haunting melody. And if you do start hearing it, either you're chosen or your microwave's haunted. Either way, hit that subscribe button before the static starts whispering back. Imagine a metronome clicking out an impossible tempo, and you understand what a pulsar sounds like if you could hear it straight from the void. Before we get into the sound, imagine a star so dense that a teaspoon of its material weighs 1 billion tons, spinning up like a cosmic blender at hundreds of rotations per second. Each time its magnetic poles sweep past Earth, we catch a flash of radio energy, an interstellar tick that, when translated into audio, comes across as a steady ping, 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 like a phantom lighthouse guiding ships through space. These neutron stars were born in supernova firestorms, with their cores collapsing into objects barely 20 kilometers across. Despite this, their magnetic fields stretch millions of times stronger than anything we can recreate on Earth, whipping charged particles into beams of radio light. As the star spins, those beams slice through space. Telescopes lock on, recording pulses so precise they rival our best atomic clocks. When you pitch them down into the human hearing range, it feels like standing inside a gigantic, perfectly tuned drum machine, with each beat echoing across light years. These cosmic metronomes are more than scary background noise, too. Astronomers use their unfailing regularity to probe the fabric of spacetime itself, testing Einstein's theories, hunting for ripples from colliding black holes, even mapping the galaxy's hidden mass. If you ever lose track of time here on Earth, Remember that out there is a lighthouse that keeps chugging along. Its ancient ticks reminding us that the universe has its own clockwork, and we're still just learning to read it. What happens when the universe's most magnetic objects throw a tantrum? Magnetar hyperflares add the cosmic equivalent of a billion megaton supernova mic drop. Imagine a neutron star with a magnetic field so intense it could strip data off your credit card from halfway across the solar system. Every few decades, one of these beasts twists its field lines to snapping point and unleashes a blistering burst of energy in X-rays and gamma rays. We can't hear gamma rays directly, so scientists translate the flicker of these hyperflares into sound waves you can actually play through speakers. It is a shattering, shriek-like roar, like glass shattering in slow motion, then speeding up until it becomes a high-pitched scream that fades into a low, resonant growl. The transition from scream to growl mirrors how the flare's intensity peaks in milliseconds and then trails off over minutes. Beyond the freak show spectacle, these hyperflares teach us about matter in its most extreme form. The crust of a magnetar is a lattice of atomic nuclei mashed together by gravity so fierce that a teaspoon weighs as much as Mount Everest. When that crust cracks under magnetic stress, it sets off vibrations called star quakes that ring through the star like a bell, modulating the flare and leaving easily observable oscillations in the data we convert to audio. In other words, each hyperflare is a sonic fingerprint of physics we can't replicate on Earth. It's a chance to eavesdrop on the universe's deadliest symphonies and decode how matter and magnetism behave at their breaking point. When Voyager 1 crossed the heliopause into interstellar space, it heard a faint, constant static that marked its departure from the sun's bubble into the true cosmic void. After more than 40 years blazing a trail out of our solar system, Voyager's plasma wave instrument finally detected a stable hiss in the 20 to 40 kilohertz band. It was so subtle that it could be mistaken for equipment noise. But it wasn't machinery at all. It was the song of interstellar plasma, billions of kilometers from home. When mission scientists pitched that hiss down into human hearing range, it became a ghostly white noise, an endless, almost soothing hiss that sounded like the ocean surf on an empty beach. Yet beneath that calm, fluctuations in the static showed small density ripples in the interstellar medium, like waves on a dark sea. Every rise and fall in volume reveals how charged particles brush against Voyager sensors, giving us our first direct audio map of the space between stars. It became the blueprint for future deep space explorers. This is now the sound signature engineers will need to interpret when our probes finally reach Proxima Centauri and beyond. You can think of it as the first audio breadcrumb that marks humanity's first steps into the galaxy. It reminds us that even in the crushing silence beyond our sun, there's still a hidden, data-rich soundtrack waiting out there, waiting to be decoded. If you've been at the docks, you've definitely seen a ship's hull groan as it cuts through the stormy seas. Now swap the ocean for plasma and the ship for Comet 67P Churyumov-Gerasimenko, Rosetta's duck-shaped sidekick. As the comet warmed near the sun, ice vaporized into jets of gas and dust, creating a cocoon of charged particles. Those particles sloshed against Rosetta's plasma wave antenna, generating whistles and trills in the 10 to 1,000 hertz range. When engineers converted that data into sound, the result was a series of ghostly howls rising and falling like wind through a haunted canyon, with rapid rattles as dense clumps of dust slammed into the ionized cocoon. Some passages feel like they came from a prehistoric bird, but others tumble into a low, grinding growl. It was almost like the comet itself was coughing and sighing. But heading a cosmic cranky goose is not as exciting as what it actually meant for the space nerds at NASA. They were able to use sonic clues from the comet to gauge surface activity, pinpoint jet locations, and even infer the density of the surrounding plasma environment. What would it sound like if two invisible titans smashed into each other across the cosmos? This is exactly what black hole gravitational waves give us. It's like a cosmic chirp rippling through spacetime itself. When LIGO detected its first signal in September 2015, it wasn't radio or plasma, but the very fabric of the universe vibrating like a gigantic drum. Let's go back a bit. Picture two black holes, each dozens of times the mass of our sun, locked in a death spiral. As they whirl closer, they squeeze and stretch spacetime, sending out ripples that race outward at light speed. Those ripples pass through Earth, subtly stretching our planet by less than the width of an atom. LIGO's laser interferometers caught the minuscule squeeze. Then scientists sped up the signal by a factor of about 100,000, so we can actually hear it. The result was a brief, spectacular whoop, rising in pitch and intensity over less than a second, like a futuristic sonar ping on steroids. It starts low and slow, then accelerates into a high-pitched crescendo before cutting off abruptly as the black holes merge into a single, larger beast. It feels like being strapped inside a warp drive engine warming up to maximum velocity. Don't think of this as a sci-fi fan service. This chirp contains information about the masses, spins, and even the distance of those merging black holes. Every rise and fall in the tone tightens the screw on Einstein's general relativity, confirming his century-old prediction. In fact, if you lean in, you'll catch hints of neutron star mergers, and maybe even exotic objects we haven't imagined yet. Ever wondered what it would sound like to eavesdrop on the universe's baby pictures? That's exactly what the Cosmic Microwave Background, or CMB, echo delivers. A hushed hiss carrying the afterglow of the Big Bang itself. Imagine tuning an ancient radio and catching not distant music, but the faint whisper of photons that have drifted for 13.8 billion years through expanding space. Satellites like COBE, WMAP, and Planck measure tiny temperature fluctuations in the CMB at microwave frequencies around 160 gigahertz. Manipulate these a bit and slow down millions of times so your ears can handle them, and you get a subliminal static. A soft, continuous murmur with subtle warbles where density ripples once formed the seeds of galaxies. In audio form, it feels like drifting through a silent desert at dawn, with a gentle breeze brushing past your ears, and distant echoes of a long-lost storm barely stirring the dunes. Every quiver in the hiss corresponds to a region of slightly higher or lower density in the primordial plasma. These tiny wrinkles would later blossom into galaxy clusters and the dark void. Listening to the cosmic microwave background is like carrying a stethoscope to the universe's chest and hearing its first heartbeat. It's a haunting lullaby that reminds you, even when everything seems still, the cosmos never truly falls silent.